equations, okay, for this class. And yeah, so as we have discussed, I would like to devote the last two classes to chapter 12, which is the distributions and transforms. That being said, actually I don't think we'll be able to get into Fourier transforms, although this is actually a very, very interesting topic. But I just suppose we don't have enough time. Let's see how it goes. Okay. Because the materials that we would like to cover is exactly the part for the delta functions, okay, and how to use delta functions to systematically solve any type of partial differential equations as long as they lead. Okay. And so everyone knows that our final exam is on what date? Next Wednesday, right? Next Wednesday, but different time in the morning. I think that's between 9 to 11, 9 a.m. to 11 a.m. That's a different time. Don't forget that. And if you miss that date, I am going to leave. Leave the campus, go to the US on the next day. So there's not going to be any chance for makeup. If you miss that exam, it doesn't mean that you're going to fail, but there's going to be very, very complicated procedure that we can go through to give you like incomplete, and then you will be able to, for example, make up for this class definitely not next semester, but next year. Okay, so please try. Yes, because this class, the partial differential equation is not offered every semester, you're aware of. Right. So if you miss that final exam, you can pick it up next year. So please don't do that. Okay. Yeah. Okay. So this is another thing about the logistics stuff is that there is one more homework. Okay, due this Sunday. But again, as I said, it's not going to be graded very carefully. As long as so the homework will be posted, and the answer keys will be provided promptly in this weekend. Okay, so as long as you can provide all of the work about this homework, then you can automatically earn the full score for this homework. It's not going to be very carefully graded. So please take it as a bonus gift for everyone for all of your hard work in this semester. Okay, any other things about logistics stuff? No? Okay, cool. Let's start talking about chapter 12. Okay, so distributions and transforms. Okay, so the center, our central topic is going to be this. Okay, let me write it down largely, the delta function. It's going to be the delta function, as we have discussed. We have discussed in several of our lectures. Actually, very explicitly. So the delta function. First of all, delta x is not a function. Okay. Although we have been keeping saying this as a delta function, but again, it's not a function. Delta function is not a function. Okay, so this is definitely the first thing. And second, why that is so interesting to us. Okay, and the second thing that we propose is that so delta function. This is tightly related to the idea of Green's function. Okay, I'm going to explain in a very short time. Okay, about what does it mean by a Green's function, because we have very briefly mentioned the idea of Green's function when we were introducing the solution to in chapter 7, the solution to the Poisson's equation. Actually, Laplace equation, Poisson's equation. But we didn't arrive at this name, okay, until chapter 7. So what does it mean by Green's function when we are referring to this idea in a broader context in PDE? What does that mean? Okay, Green's function. And if you have the Green's function, then you will automatically obtain the solutions to arbitrary. Okay, Green's function for let's say Green's function for a selected type of PDE. Okay, so let me frame it as for a selected PDE problem. Then you will be obtaining the solution, okay, with the Green's function for that selected PDE problem. Then we'll be obtaining the solution to that problem. We'll be obtaining a solution to that problem. Okay, but actually we have already tasted that flavor for a little. Okay, when we were discussing the idea of using the Green's function to solve the Poisson's equation in the last lecture. But to see why this type of logic chain is very generic, okay, let's actually start from ODE. Okay, let's actually start from ODE instead of PDE. So let's start from something that's called first of all, an inhomogeneous. Okay, an inhomogeneous ordinary differential equation. So more specifically, let's say we're having something like, okay, so x prime, so x is a function of t. Okay, x is a function of t, and we are actually trying to solve some certain questions. That's something like x prime prime plus ax prime plus bx that equals to something like ft. So that's a bit. So if the right hand side is 0, okay, if the right hand side is 0, then that's actually, this question is so easy to solve. Right? You can just use the, I believe that you have enough weapon to tackle this question. Okay, but the problem is that we are having a right hand side. Okay, we are having a annoying right hand side. So how do we obtain? The question is that, so first of all, you see, so can anyone tell me, usually what did you do in your ODE class to tackle that kind of question? Suppose that the f is given.
Guess the form of x first, and then we set up some unknown parameter. And
guess the form of actually a specific solution. Guess the form of this. So because the generic solution, the general solution to the homogeneous solution when the right hand side is 0, that's actually easy to obtain, right? Then what we actually need is a form, a specific solution, right? We simply need a specific solution targeting to tackle the right hand side, the inhomogeneous right hand side. But it's actually, so the first comment is that it's generally, it generally needs extra work. To tackle the f, so the inhomogeneous ft, right? For example, if f is a polynomial, but if f is a polynomial, I'm asking you yourself to try to remember, try to recall some of the things that you have learned in your ODE class. So if f is a polynomial, what would you guess? For x, for the specific solution. You also guess x is also a polynomial, right? Because second order of x is still a polynomial of t. Okay, this is still a polynomial, this is still a polynomial, then left hand side is a polynomial, right hand side is a polynomial. Right? You will guess x is a polynomial. If my f is an exponential function, what would you guess? Okay, I will also guess x is a similar type of exponential function, right? If my f is a sine or cosine function, what would you guess? Similarly, a triangular function, a linear combination of sine and cosine. This is what we're going to do, right? But again, let's see. This depends on what? This actually depends on our a priori knowledge about, okay, if f is what, then I guess x is what. This is like a pattern matching. This type of method is not generic at all. For example, if I change my f to be something like really complicated, okay, then actually, even if you could use such a guessing method to obtain a specific solution of x, actually it requires such a complicated computation, right? So what we are trying to propose today is that, okay, because you see, what we are trying to propose today is actually a generic framework that works for, even if not arbitrary, but still a large, but a very broad category, okay, of linear differential equation problems, including both ODE and PDE. Okay, that we could. So now let's look at this question again. So again, let's try to get very clear our motivation. What's our motivation? Our motivation is that I would like to, like a method that solve equation star, okay, when f t is arbitrary. I would like a method for that. But how is that even possible? How is that even possible? Well, delta function makes it possible. Delta function makes it possible. So you see, what is the can anyone remind the class what are the properties of the delta function? What are the properties of what's okay? So let's say I'm having a delta function, then what property does this function have? Can you please say it out? So say it louder. Go ahead. Don't stare at other people. You were trying to remember something, right? Come up with what you were just saying.
It kind of looks like that, right? Like what goes to...
Try to use more mathematical rigorous language.
Either infinity at 0, right?
Okay. So delta t satisfy what? Delta t equals to
infinity.
Okay, infinity when
T is
t equals to 0 and
1. 0.
0. Okay. When
T
t is not 0. Okay, very good. So this is the first piece of first property. And then anything else? Is that all? Is that everything that characterizes my delta t? What else? It should be integrating up to 1, right? Okay. So the integration from negative infinity to positive infinity, my delta t, okay, is actually dt is actually 1. And one more comment about this is that since we already know that delta t is 0 in most of the places, so this integration actually doesn't have to take place from negative infinity to positive infinity at all. It can just take place around 0 where it has non-zero masses, right? So that's actually equivalent to something like, okay, the integration from negative epsilon to positive epsilon, delta t dt equals to 1. Okay, is that everything that you know about delta function? What else that you know about delta function? Of course, these two things already, later we're going to see that these two things already successfully characterize the delta function, but what else do you know?
The antiderivative of the heavy sum?
Sorry?
Is the antiderivative?
Okay, so, okay, that's also useful. And let me put it over here. So, and you were saying something like antiderivative, well, so why don't you just use the integration? Or let's say in the reverse way. The first order derivative of function is delta function, okay? Then we can just say that, okay, if I'm having a Heaviside function, ht, okay, then its first order derivative is exactly my delta function, or more specifically, my ht is exactly the function like exactly equals 1 when x is non-negative and 0 when x is negative. It's actually like this, like a step. Right? This is also called a Heaviside step function, but I guess I don't need to repeat this thing that you already know. What else can you know?
Convolution.
Convolution. Okay, that's actually, thank you for that. Convolution is actually one of the most important properties that will be quoted later. Okay? So convolution. Can you say it in a more specific way about what does the convolution work? You just mentioned convolution.
The convolution. I'm not sure if I remember it correctly.
Right, just say it.
The convolution, the function itself.
Convolution of what and what is itself. Can you say it more clearly? The convolution between delta function and an arbitrary function is that arbitrary function itself, right? So let's say for an arbitrary function ft, okay, for an arbitrary function ft, but of course, this function needs to have the same independent variable. Okay, otherwise it doesn't make any sense to do the convolution, right? Okay. For an arbitrary function ft, well actually later you're going to see that this function is not that arbitrary. Okay, it's not that arbitrary, but again, this is not a functional analysis class. Let's just ignore these technical details for now, okay? Let's say for an arbitrary function ft, then the convolution, okay, f convolution with delta is also a function of t, right? This function is f itself. Or more specifically, this actually equals to the integration from negative infinity to positive infinity ft, and then multiplied by delta, okay, s minus t ds. This again equals to, oh, sorry, my bad. I should put in, actually I should put in this one. Yes, you're right. Fs, and then this is going to be t minus s. T minus s. And that equals to ft. And since the convolution is interchangeable, the convolution is interchangeable. A convolute with B is exactly B convolute with A, right? So this can also be written into something like from negative infinity to positive infinity, okay? F t minus s, okay, and then delta s ds. This is the same thing. Ft. Same thing. Okay, these are four of the most important properties, okay, for the delta function. Now, that's with these things in mind, let's revisit this inhomogeneity. You see, again, what was the things that we were, what was our largest challenge? Ft. It's the Ft, right? It's the Ft that we were not so happy about. But you see, if Ft is something that we are not so happy about, so again, why we are not so happy about Ft? That's because of its arbitrariness. We don't know what it is, okay? And we didn't have a very good method to handle Ft. If Ft is going beyond the prescribed, our prescribed database of the function, the polynomial functions, the exponential functions, the sine and cosine, if it goes beyond that category, okay, then we don't know how to deal with Ft for now. But now, let's look at our dictionary of the delta function. What is possibly related to Ft over here? What is possibly related to the arbitrariness of Ft over here? Which one of the problem that you think that's going to be? 1, 2, 3, 4, which one? The fourth one, right? Because the fourth one really tells you that for an arbitrary Ft, okay, my Ft can be regarded as what? My Ft can be regarded as a convolution, okay, between itself and delta function. What does this really mean? Well, you see, first it's possibly a good idea for us to look into what does it mean. What are the physical interpretations of these two things for now? Of course, let me do some spoiler over here. Of course. So before we move forward, let me just give you some spoiler, okay? I'm going to directly tell you what we're going to do next, and then I'm going back to explain why we're going to do that. Okay? So spoiler. So we will first, so in order to, okay, so spoiler, so it's actually, we're going to give it a rectangle over here. Probably we'll be needing larger space, okay? So in order to solve x prime prime plus ax prime plus bx equals to ft, okay? We will be solving, okay? We will first derive, okay, a Green's function, gt. Okay, we'll be first deriving a Green's function gt. So what does this gt satisfy? This gt exactly satisfies that. Okay, actually, let me put it as GST. Okay? Let me put it as a GST. So this GST exactly satisfies that, okay, GST prime prime, okay, plus a GST prime, and then plus B GST, exactly, okay, equals to what? Exactly equals to delta T minus S. It exactly equals to T minus S. Well, since you see, since in this case only, my A is, assume that my A is temporally homogeneous. Temporally homogeneous. B is also temporally homogeneous, which means that A and B are both constants. If A and B are both constants, actually I'm free to remove these S because I will just be able to do some spatial translation from my G to obtain a different version, okay, of the GST. Okay? So in this case, these things, it's adequate. Okay, in this case, it's adequate. It's adequate to just solve GT prime prime plus AG prime T, okay, and then plus P GT, which is the delta T, and then obtain then GST will be automatically equals to GT minus S. Just do spatial translation. We just need to do spatial translation from G to obtain GST. But again, this is all because my A and B, they are temporally homogeneous, they are constants. Okay? If I could obtain this GST, then what do I get? Then, you see, how do I go from, you see, this is the right hand side, right? Let's compare these two equations. This is the right hand side. This is the right hand side. This is the right hand side. This is left hand side. This is the left hand side. Again, now I have already obtained GS, right? I have already obtained GS by solving this equation, the equation for Green's function. I have already obtained my Green's function. The question is how to obtain S, which is the solution to the original E. Right? This is my motivation. But you see, the first thing is that how do you relate the right hand sides? If you have a delta function, how do you go from a delta function to ft?
Times fs, then do the integration.
Right? You just need to do. Okay, then you see, because you see f. How do we go from delta t minus s to ft? How do we do this? We just need to do such things like, okay, let's quote what we have over here. We just need to do ft equals to, okay, the integration from negative infinity to positive infinity fs, okay, multiplied by delta t minus s ds. So good? Okay. Then what about the left hand side? What about the left hand side? What about the left hand side? You see, what does the right hand side mean? What does the right hand side mean? The right hand side is telling you something like, okay, if I have, so the right hand side tells you that, okay, so what is fixed over here? P is fixed, delta is fixed, S is moving. So the right hand side is basically telling you that, okay, I am actually having delta t minus s, okay, for I have delta t minus s for s equals to, let's say, from negative 100, negative 99, negative 98, and equals to 0, 1, 2, until 99, until 100, and of course other numbers, rational numbers, in these rational numbers, irrational numbers, I have the delta function for everything. Okay? And these delta functions are exactly working as the building block for my ft. Just like when you are, well, just like when you are putting a Lego, right? Just like when you are putting a Lego. So what does that mean? So you see, again, this is my ft. Okay, this is my ft. What is my delta t? My delta t is a Lego. Is a small. Let's say my delta t is the smallest pieces, okay, of a Lego. So first of all, my ft can be regarded, approximately regarded as a combination of these chops, right? My ft can be regarded as a combination, linear combination of these chops. I have many chops, and each chop can be regarded as what? Each chop can be regarded as. First of all, I am having a Lego. I'm having a Lego. How many Lego that I need to complete this chop? Exactly, so let's say this part is x0, then this part is fx0, this part is fx0, so that's a Lego, okay? So how many Legos? My Lego is exactly the delta t. How many Lego that I need to complete this chop? I exactly need 1, 2, 3, 4, 5, 6, until fx0. I need that many Lego to complete this job. Okay, and then if I'm done with that, then I'm done with one chop. So that specifically is the ft minus, in this case, is ft minus x0 multiplied by fx0. Okay, but I need what here? The integration goes from what? Well, the integration goes from negative infinity to positive infinity. Just like here, if I need to reobtain the full information for the ft, what I'm going to do? I actually need to complete all these chops, all these other chops, right? And every single of these chops are made up by the Lego. So that's good. So you see, on the right hand side, here, from the right hand side, I am using my delta t minus s is my Lego, and I am using my Lego to complete ft. And the specific way that I did it is to actually, this is actually a linear combination. This can be regarded as a linear combination for all the possible delta t minus s when I'm fixing my t and valuing my s. So that's good. Here, because you see here, fs can be regarded as what? Fs can be regarded as the weight. Oh, sorry. This is the weight of Legos. This is my Lego, right? My ft is actually can be regarded as a linear combination of all these Legos. This is how I am solving. This is how the right-hand side is done. Then what does this equation mean? This equation means that now for every single Lego, which is the delta function, for every single Lego, what have I done? I have solved the corresponding Green's function. Therefore, in order to recover, you see on the right-hand side, to recover f, I need to sum up these Legos in a linear combination fashion. And therefore, but it's in exactly the same way on the left-hand side. If I want to recover x from my G, I just need to do exactly the same thing. I just need to do exactly the same thing. Or more specifically speaking, in the mathematical way, this is what I'm going to do. So again, let me first write down the two right-hand sides, right? Okay. So which is that ft that will be exactly equals to the integration from infinity to plus infinity fs delta t minus s ds. I'm just simply copying what we have already known okay, about the delta function. Okay. Okay, what do I know about ft? What do I know about ft? Ft is exactly the right hand side of my target equation, right? So therefore, my ft this guy actually equals to x prime prime plus ax plus prime plus bx. This is my ft. Okay. What do I know about delta t minus s? What do I know about my delta t minus s? My delta t minus s is exactly the right hand side of the second equation, right? So what I'm going to do is that, okay, now this guy equals to, from negative infinity to positive infinity, fs is going to stay, but the delta t minus s, okay, is going to be replaced by the left hand side of the second equation. And therefore, I will be obtaining something that's called, okay, here it's going to be gs prime prime t, and then plus a gs t prime, and then plus b gs t ds. So far, so good? So far, so good? Is everything okay? Is everything okay? I'm simply replacing this, okay, by the left-hand side of the Green's function equation. Nothing else is done. Nothing fancy is done. So is it good? Okay. And in this case, but again, you see, in this case, since my a and b are constants, okay, therefore these GST are actually what they can be obtained from GT by just simply doing some spatial translation, right? Again, I will be rewriting the from infinity to positive infinity fs, okay, here GT minus s prime prime plus a gt minus s prime, and then plus b gt minus s ds. Okay, bracket. Everything okay? This step is okay? Sounds good? Sounds good? Ha ha! One more thing. Okay. What do we know about fg? Okay, so this actually, let me first write down, okay, my ha, let me first write down everything over here. So this actually from negative infinity to positive infinity, f s g prime prime t minus s, okay, and then plus a from negative infinity to positive infinity, f s g prime t minus s, and then plus b from negative infinity to positive infinity, f s g t minus s. Of course, ds, ds, ds. This part is good? Yes, go ahead.
I just have one conclusion because when you mentioned d sub s is a one-level function and d prime prime sub s p is the second derivative of p. But when you move s inside, it's a two-level function. I mean, when d prime prime t minus s, we actually.
No, so I'm sorry. Okay, so sorry about the confusion over here. This is because this is because s is actually regarded as constant, and t is the variable. T is the independent variable. So when you are doing actually for g t minus s, when you are doing the prime and doing the prime, it doesn't as long as your s is fixed, then actually it's just going to be spatial translation. Okay, so that's good. Okay, one more step. This is going to be look like what? This is going to be look like. Okay, so you see, first of all, what do you say about because this might be a little bit hard, a little bit indirect for us to directly see the first two terms. Where does the first two terms go? But what is the last term? What is the last term? Fs multiplied by gt minus s. This is a very canonical structure of what? Convolution. Convolution between what and what? Convolution between what and what? and what? G, right? The last one is exactly BF convoluted is G. So far, so good? What about the first and second one? If we don't look into the prime over here, G prime of T minus S, this is a function, okay, whose in the bracket there's going to be T minus S. Here, this is a function, okay, this is a certain function, T minus S. Therefore, these two integrations are also what? Convolution. But this is a convolution between what? F and G prime prime. This is a convolution between F and G prime. Okay. So I'm safe to write down something like F, okay, convoluted with G prime prime plus A F convoluted with G prime. So good? So good? Okay, now it's time for us to compare our last results with the beginning. What's my left hand side? My left hand side is x prime prime plus ax prime plus bx. My right hand side is f, the convolution between f, g prime prime, and then plus f and g prime. And then plus the a multiplied by the convolution between f and g prime, and then b, f, and g. So that's good? Okay. So let me write two things down, okay? So the first sum is x prime prime plus ax prime plus bx. The second sum is f convoluted with g prime prime, and then plus a f convoluted with g prime, and then plus b f convoluted with g. What do you want to guess?
X equals to F convoluted.
This is what we hope. This is exactly what we hope, right? This is exactly what we hope. We hope that, okay, we hope that x equals to this, my x prime equals to this, and x prime prime equals to this, right? Right? Because if this is done, if this is done, then actually I can solve I can solve my x from f convoluted with g. Because I already know what? I already know f. It's an arbitrary function, but it's given. We just don't know specifically what it is for now, but it's given. Okay? G is what? G is what we directly solve. G is what we directly solve from this equation. Right? G is something that we already solved. So on the one hand, I have my f to be already given. On the other hand, I have my g, which is solved by our hard work. Convolution, and we're done. One convolution, and we're done. Convolution is an operation that we know. Okay, what else is not there? But we are still not there yet. We are still not there yet. What do we need to confirm to make sure that x indeed equals to f, the convolution between f and g?
Uniqueness.
Go ahead.
Uniqueness.
Sorry?
I think it's a uniqueness.
Uniqueness, yes. Uniqueness is something is one thing, but here you see, we haven't. Another thing that we haven't confirmed is that, you see, although this looks like some x plus a something plus b something, this also looks like something plus a something plus b something, but we haven't proved yet. We haven't proved that x, we haven't proved that f, you see, this is actually f convoluted with g prime. This is a convolution between two functions. One thing is f, and another thing is g prime. We do not know yet that this equals to f g prime. We don't know this. See, we don't know this yet. And also, we haven't confirmed that f convoluted with g prime prime equals to f convoluted with g prime prime. We haven't established this yet. Because you see, if these two things are confirmed, then it's basically telling you that the first one is x prime prime plus 8x prime plus bx. And the second thing is actually another thing called y prime prime plus ay prime plus by. And these two things are equal to each other. And now if I have my unique diagram, I'm done. Right, but I haven't established this yet. Okay? See, I haven't established this yet.
Can I ask two small questions?
Go ahead.
Actually, we define the G, right? Do we call it Green's function or?
Yeah. We are going to call this as
Actually, this G can be solved.
Yeah. This actually.
by Laplace transformation.
We're not there yet. Thank you for the spoiler. But actually, the solution of G actually is not can be derived from traditional methods. It can actually be derived from traditional methods.
Is this G a function?
Sorry.
Is this G?
Yes, G is a function. In this case, G is indeed a function.
Um,
But the problem is that G might actually be indifferentiable at some point. It's actually piecewise differentiable, exactly because of the existence of the delta. So that's good. Okay. So these are the last two things. These are the last two things that we need to verify. Okay. Can we verify that? Can we verify that? Well, you see, okay, so what is F convoluted with G is what? F convoluted with G is from negative infinity to positive infinity, Fs, okay, G, T minus S, ds. This is a function of what? This is a function of T, right? Then F convoluted with G, this is a function of T. What is its derivative? What is its first order derivative? I take derivative to what? On the right side, to T, right? It doesn't have anything to do with my F over here. It doesn't have anything to do with my S over here, right? So indeed, this actually equals from negative infinity to positive infinity, Fs G prime T minus S ds. Again, this comes from at the beginning of this class. We have our liberty to exchange the order of integration and exchange the limit, the order of limit, as much as we want. Okay. So here, we need to first take the derivative for the whole integration, but now we're just simply switching the order to take the derivative at first, and then integration. What is this? This is indeed my F with G prime, okay? Which is exactly F convoluted with G prime. Or to be a little bit more rigorous, okay? To be a little bit more rigorous, I don't want to abuse the notation because this is the first time you folks are touching this, right? So F convoluted with G prime. This is a function of T, okay? F convoluted with G prime. This is a function of T. So that's good. Therefore, we have proved that, xt exactly equals to what? Xt exactly equals to F convoluted with G. T. Okay. F equals to F convoluted with G, T. Again, F is something given. G is something that we're going to solve. Okay, G is something that we're going to solve. And then do a convolution. Then we obtain the solution to this equation for arbitrary right-hand side F. So is it good? Okay. And now, addressing your question, how to solve that? How to solve this equation? Well, you see, this is actually a side topic because I actually didn't have any plan to dig into this. How to solve this equation, but let me try to use 1 or 2 minutes to very briefly, cover the strategy. So you see, delta T minus S has what kind of property? According to the properties over here. Delta T minus S has what kind of property? It, again, is almost everywhere 0, right? It's, again, almost everywhere 0. So, that means that, when T is smaller than S, what does this equation mean? when t is smaller, because here I'm going to solve this equation for a specific choice of s, right? For a specific choice of s. So now when t is smaller than s,
It's a homogeneous.
it's just a homogeneous equation, and you know how to solve it. When t is larger than s,
Still homogeneous.
still homogeneous. The problem is that how do you get across the s over here? Right, so let me write what I just said down. So when t is smaller than s, okay, gs prime prime t plus a gs prime t plus b gs t equals to 0. Right, equals to 0. Okay? And when t is larger than s, when my t is larger than s, gs prime prime t plus a gs prime t plus b gs t is again 0. Okay, is again 0. And what you're going to see, what you're going to see is that, okay, both these two things, has exactly the same form as a homogeneous equation, okay, but actually they will lead to two different specific solutions. This is because, imagine that I am having f and f, sorry, I have already used f. What is good to use? Let me use eta, okay. Let's say I'm having my eta 1t and eta 2t as the general solutions. Okay. Let's say I'm having my eta 1t and eta 2t as the general solutions to this homogeneous equation. This is completely okay, right? Okay. Then anyone has any question about this? I'm having a homogeneous solution. I'm having a homogeneous solution, and this is the second order ordinary differential equation. So it's very likely for one. Well, I will absolutely come up with two linearly independent a general solution. Okay? And the general solution will exactly look like, okay, which means that GST will look like A1 eta 1 t plus A2 eta 2 t, okay, for t be smaller than s. Okay? And GST, it will look like A2. Oh, sorry. Let me use B1. Let me use A2. And here let me use B1. B1 eta 1t, and then plus B2 eta 2t, okay, for t be larger than s. Okay. Then we will be needing to carefully tackle the relation between A1 and B1, A2 and B2 to fulfill the request of the delta function over here. Because of what? Because if the delta function were 0, if we were not having a delta function on the right hand side, but we were having a 0, then of course everything is so continuous. So I should exactly have my A1 equals to B1, A2 equals to B2. But I'm having a delta function over here, which means that, okay, after taking these derivatives, here, my GS is a function of t. After taking the derivative, it actually has to have a sharp jump. It has to produce a delta function, okay, exactly at t equals to s. Therefore, that means that my A1 and B1, A2 and B2, they are going to be a jump. There's going to be a jump. So good? This is how you solve it. But again, this is not required by this class. This is not required by this class. I'm just showing you the general. Okay, so again, if there's anything that you would like to take on, none of these things belong to our PE book. Actually, should have been covered by ODE or not, but it doesn't really matter. So the take-home message over here is that, okay, the delta function with these properties of the delta functions in mind, okay, we are able to systematically use delta function to crack down, okay, a large group, okay, of ordinary differential equation. And as you might have already observed, actually, the delta function over here, the delta function method over here, it is not restricted within this specific type of ODE, right? Imagine that I am having an arbitrarily linear order. So now imagine I'm talking about an inhomogeneous question for a arbitrary ODE, arbitrary order linear ODE, which is something like x, the nth order derivative, okay, let's say an, and then plus an minus 1, x, the n minus 1's order of derivative, and then plus an minus 2, x, the n minus 2 order of derivative, and then plus plus a1 x prime plus a0 x, okay, which equals to ft. Imagine that I'm having something like this. Imagine I'm having something like this. Then the same philosophy, okay, can be applied again. The exactly same philosophy should be applied again, which is that, okay, first step one, okay, which means that step one, we obtain a GST, okay. Now, a and GST the nth order times a n minus 1 GST the n minus 1's order times and plus plus a1 GST prime and then plus a0 GST, okay. Delta t minus s. I first obtain a Green's function satisfy this equation, okay, and then step two, okay, solve the equation about the Green's function, okay, and then step 3 is that my xt will be exactly the integration from the infinity to positive infinity, okay, fs g t minus s. Yes. Right? Right? Why that could happen? Why that could possibly happen? You see, as I have explained using the analogy, okay, as I have explained using the analogy of Lego, let's see exactly, okay, with the idea of linear operator, that we have learned at the beginning of this semester. Let's use that mindset, okay, to understand what's really happening over here. You see, the left-hand side is actually doing what? The left-hand side is actually doing what? I have certain function that I don't know, x. I'm taking derivative, okay, and then do a linear combination. After all these operations, I say I obtain something that's called ft, right? So, from the perspective of linear operator, I'm actually having something like L. Okay? L is sending x to a function f. Okay, L is sending f. Okay, so let me or to be a little bit more specific, let me do this. Okay, L is a linear operator that is actioning on functions that are about t. If you give me x, if you send x to this operator L is going to return you something that's called ft. So much good. This is the logic. This is the methodology that we introduced in the first class of this semester. Okay, and of course my L is exactly something like a and okay, and then the nth order derivative, okay, and then plus a n minus 1, the n minus 1's order of derivative, okay, and then plus okay, I guess I don't need to repeat the setting. This is my help. So far so good? So far so good? So, in linear algebra, let's say in linear algebra I'm having something like Lx, okay, that equals to f. Yes, equals to f. X now is not a vector. F is not a vector, right? And I would like to solve this linear problem, okay, which x can be sent to f. So far so good? So far so good? But the problem is that this question probably sometimes is not that easy to be tackled. It's sometimes probably not that easy to be tackled. But, you see, my f equals to what? My f actually equals to something like f1, f2, until fn. So what's it? This is my f, right? If I am able to compute let's say Lx1, that equals to 1, 0, 0. And I am able to compute which x2 gives me 0, 1, 0, okay? And I can compute a x3 that is something like 0, 0, 1, 0, 0. And finally, Lxn that equals to 0, 0, 0, 1. If I am able, so you see the original linear problem is a little hard, but if I am able to obtain to solve these sub-questions, if I am able to solve these sub-questions, which means that I am able to obtain a x1 solving the right hand side, so L is sending x1 to the first unit, the first unit vector, sending x2 to the second unit vector, sending xn to the nth unit vector. How do you propose to obtain our x? Then what is my x? If I already know x1 to xn, what is my x? A linear combination, specifically that should be what? f1 multiplied by x1, f2 multiplied by x2, until fn multiplied by xn. So far so good? Okay. So my x can be written as f1 multiplied by x1 plus f2 multiplied by x2 plus plus fn multiplied by xn. Okay, or in a summation I from 1 to n fi xi. This is my x. So where do we go? So where do we go? Well, this, you see, here, you see, let's compare these two things. This is a linear combination. This is also a linear combination. Here, in the linear combination of vectors, we are utilizing what? The coefficients are what? The coefficients are exactly the coefficients for my f. Here, above, in the linear combination of the Green's functions, the coefficients are what? Are exactly my f. See, this is the logic. This is why the idea of Green's function will work. This is generated, but again, you see, this depends on what? Everything that I said depends on if we could successfully solve and actually come up with a generic formula for these xi, right? It depends on if I could really successfully solve the x1, x2, x3, xn. And not only that, I wish I could use only one formula to represent all these things. Otherwise, I would have to solve m problems. Right? Otherwise, I have to solve m problems. So the successfulness of the idea of the Green's function all depends on if the Green's function can be solved. Once it is solved, we're done. Once it is solved, we will be able to recover. Okay, we'll be able to recover the solution that we are hoping for. Okay, by linear combination of the Green's function. So that's good. So why don't we take a 5 minutes break, and then we will resume after the break.